It's David Spears, Civil Engineering Instructor at Texas Tech University, talking about a recent CE 3303 solids exam. We've got a transverse shear and shear flow problem of where we're reinforcing or increasing the moment of inertia carrying capacity and the shear carrying capacity of this steel beam, this blue I-shaped W18 by 35. The beam itself, the blue beam, starts off with a moment of inertia of 510 inches to the fourth. But we're going to reinforce it by adding these plates on top and bottom that are 6 inches wide and half an inch thick. We're going to bolt them to the flanges using 0.75 inch diameter bolts with a longitudinal spacing, that means along the length of the beam, of 10 inches. We're given that the average allowable shear stress in the bolts is 12 ksi. Okay, so that's saying that the average shear stress means tau shear stress V over A. Average shear stress is V over A. It is not VQ over IT stress. Anyway, it's said to be 12 ksi, and then we're given the moment of inertia for the composite beam. That means that's what shear flow is all about, making a composite beam out of multiple pieces and parts and connecting them with enough connectors to create shear flow that engages the full beam action, full bending of the beam, so it all works together. So that moment of inertia is 1025. We don't care about the moment of inertia of the beam itself before it gets reinforced, because this is a composite beam problem, a shear flow problem. Okay, so we look on the equation sheet and we get these two basic formulas that are really connected, said to be equal to each other. Shear flow is equal to little q, which is VQ over I, and that's also on the equation sheet it shows as V connector times divided by the spacing S. Okay, so we're given, or the means to calculate all but one of these numbers. So what we're looking for is, in number 8, determine the largest possible vertical shear force, which is the shear force in the beam that it can withstand based on the spacing of those connectors, the connector's strength, and the composite section of the beam, built-up composite beam that we're building up. So we're looking for an answer in something like kips, probably, by this factor that it's a shear force. And that is that number right there. So we can figure Q is y bar prime A prime. We're given I. We can figure what the connections are worth. And there's 2 of them. And then we're given the spacing. So I'm going to rearrange this equation, and I'm going to say what I'm going to be figuring is V is equal to the shear force carrying capacity of that composite beam is V is equal to V connection times I divided by Q divided by S. So that's the main formula. Well, I don't know what the V connection is. I need to look at the number of fasteners, which there's 2, top and bottom, at a spacing of 10 inches. So I need to see what V connection is. Okay, that says that each bolt has an allowable shear stress of 12 ksi. So I'm going to use the fact that tau is equal to V over A, because it said it's average shear stress, rearrange that, and say per bolt, each bolt is good for a shear force of tau times A. Just rearrange that equation. Well, tau is said to be 12 ksi, kips per square inch. A is the area of one bolt. Well, it's a 0.75 3/4 inch diameter bolt, so it's pi over 4, 0.75 squared gives me the area of one bolt. So that works out to be 5.30 kips, because I've got inches squared here for that area. So each bolt is good for 5.3 kips. Remember, that's a force, not a stress. And that's what V connector is in this thing. It's a force in the basic formula. So now I know that, I can say V, the shear force allowable on the beam, is V connectors, which there are 2 of them to connect one plate. So I've got 2 connectors, 5.3 kips each. I is that 1025. S is the spacing, 10 inches. And Q is the Y bar A prime thing. Okay, so Y bar prime is the distance from the centroid of A prime. A prime is, for that plate, it's the area of one plate, because I'm trying to engage it to act as a beam, composite beam, with the blue wide flange W18 by 35. So the area of that thing is just A prime, and that's 6 times 0.5, or 3 inches squared. Y bar prime is the distance from the neutral axis, which is right here in the center of this composite beam. It's symmetric. So it's 18 inches total, tall. So the distance to the bottom side of that plate, or the top of the flange, is 9 inches. Half of 18. Then the centroid of this plate is right there, 0.25 inches down from the top, or up from the bottom of the plate. So I've got this distance right here, which is 0.25 inches, half the thickness of the plate. That makes Y bar prime this distance right here, which is equal to 9 plus 0.25 inches, 9.25. Therefore, I've got all my numbers for my calculation. Q is Y bar prime, 9.25, times A prime, 3. I've got kips on the top. I've got inches to the 4th on the top. I've got inches for spacing, and Q is in the units of inches cubed. Everything cancels out except for kips, and the answer turns out to be 39.2 kips.